Let's play a little game. Think about optimizing a tire rim, analyzing the fuselage of an aircraft, simulating a bio-waste incinerator, designing a massive gas carrier, and predicting the airflow over a greenhouse. I mean, what could these projects possibly have in common? On the surface, it seems like nothing. But if you look a little closer, they all share a powerful set of tools. It's kind of like a secret language that modern engineers use to solve just about any problem you can throw at them. So let's ask that question again, but a little differently. What really connects an airplane wing, which is all about slicing through the air, a shipping container built for pure brute strength, and a greenhouse engineered for a super delicate environment? Well, the answer isn't a single object. It's a way of thinking, a toolkit of digital methods that lets us see the invisible and honestly build the impossible. So, in this explainer, we're going to decode that secret language. First up, we'll get the vocabulary down. Then, we'll see how that vocabulary is used to make things lighter, faster, and stronger. We'll also dive into how engineers master invisible forces, like air and water, how they tame extreme conditions, and finally, how this whole toolkit is literally building the future of manufacturing. So, let's get into it. First stop, that secret language. To really see the patterns that connect all those different projects, we've got to understand three core concepts that engineers are using every single day. Everything really kicks off with optimization. This is the big goal for pretty much any design. See, it's not just about making something that works, it's about making it work in the best possible way. It's this constant balancing act, right? Making something lighter but not weaker, or faster without guzzling fuel. It's the whole philosophy of doing more with less. Next up is finite element analysis, or as you'll always hear it, FEA. The best way to think about this is like a digital crystal ball, but for solid objects. It lets engineers ask, what if, 1,000 times over, before a single thing is ever built? What if we double the load? What happens if it gets super cold? What if we swap out the material? FEA spits out the answers in minutes, not months. It's a total game changer. And our third key term is computational fluid dynamics, or CFD. If FEA is the crystal ball for solids, then this is the virtual wind tunnel. CFD lets engineers see and analyze the invisible world of fluids. We're talking air flowing over a wing, water rushing through a pipe, that kind of thing. It's how they can test a dozen different shapes to find the one with the least amount of drag, all on a computer before they even think about cutting metal. Okay, so now we've got the language down, let's see it in action. The very first pattern you start to see everywhere is this relentless, non-stop quest for optimization. This is the driving force behind everything. In a world with limited resources and a constant demand for maximum performance, efficiency is king. Every single gram of weight you can shave off an airplane is fuel saved. Every bit of strength you can add to a shipping container means more cargo it can carry safely. And what's so wild is seeing how this one idea of optimization just pops up everywhere. It's used to slash the weight of a car's tire rim, to refine the shape of a plane's body and its winglets, and even to optimize the internal support structures, they're called scantlings, of a gigantic oil tanker. We're talking completely different industries, different scales, but the exact same fundamental goal. And the end result? It's a total transformation. Optimization takes a design from just being functional to being highly efficient. It takes something heavy and makes it light, but just as strong. It refines a standard, clunky shape into one that slices through the air with less resistance, turning what would have been wasted energy into real, measurable performance. So we've optimized the solid parts, but what about all those invisible forces that are constantly pushing and pulling on them? Well, this brings us to our next big pattern, mastering the flow using CFD. This idea is absolutely crucial. Doesn't matter if it's a car, a plane, or even a skyscraper. It exists inside a fluid, usually air or water. And that fluid is always pushing and pulling in really powerful ways. So to design something that's truly effective, you have to understand and work with those invisible forces, not fight against them. And this is where the sheer power of CFD just blows you away. Of course, you see it in aerospace, analyzing the aerodynamics of a drone. But the range is just incredible. It's also used to perfect the flow through a high-powered industrial water jet nozzle, to improve how well waste burns inside an incinerator, and even to figure out the best way to cool a greenhouse. It's the exact same tool, applied to completely different worlds. All right, now for our third pattern, engineering for the absolute extremes. This is all about designing things that don't just perform well on a good day, but can survive intense heat, brutal cold, and just unbelievable physical forces. Thermal analysis isn't just about things getting hot. It's about managing the entire spectrum of temperature. Engineers use it to analyze a superhot coolant pipe to make sure it doesn't fail, but they also use it to design a carrier for liquefied natural gas, which has to be kept at a mind-bogglingly cold -162 degrees Celsius. And they even use it for precise control, like figuring out how to make our food last longer in storage. And this is where FEA basically becomes a survival tool, especially in the maritime world where the forces are just staggering. Engineers use FEA to make sure a ship's hull won't buckle under pressure, that it can handle all the twisting loads from rough seas, and that critical parts can survive intense vibration. They even simulate the absolute worst-case scenarios, things like collisions and, get this, underwater explosions, all to make these vessels as safe as humanly possible. So, we've seen the toolkit. How does it all come together? Well, our final section looks at how these digital tools are paving the way for the next wave of innovation, especially in something called additive manufacturing. You probably know this by its more common name, 3D printing. Instead of the old way of starting with a big block of material and cutting stuff away, additive manufacturing builds complex objects from the ground up, one tiny layer at a time, straight from a computer file. And what's so cool is that this whole process is a perfect marriage of our entire toolkit. It all starts with a digital design, right? One that's often been heavily optimized. Then, during the printing itself, thermal analysis is critical to make sure the material melts and fuses together perfectly without warping. And finally, FEA is used to double-check that the finished printed part has the strength it needs to do its job. It's the entire engineering language we've been talking about, all working together in one process. So, looking back at that long, kind of intimidating list of projects from the beginning, it wasn't just a random collection at all, was it? It was a perfect demonstration of how modern engineering is really just a super versatile toolkit. The same core ideas, optimization, FEA, and CFD, are being used over and over again to solve problems in the sky, on the road, out at sea, and inside our factories. The exact same tools that shape an aircraft wing are also shaping the tiny nozzle of a 3D printer and making sure a tanker ship can survive a monster wave. That's the hidden pattern. So now that you've been let in on the secret language, take a look around today. In the car you're driving, the bridge you cross, the phone in your hand, where are you going to spot these powerful ideas at work?